All right, folks, good morning. So usually the day after the exam, I try to get exams back to you guys. But I'm not doing that today for two reasons. Reason number one is there's still a couple of you who have to take it. They've made arrangements with me to take it outside of the standard time, so I'm going to delay going over that exam uh, for their benefit. And the second reason is just because, good God, normally my exams aren't due at midnight, and there's no way I'm going to get stuff graded before morning if you guys don't do them until close to midnight. So wow. So I'll try to get those back to you either tomorrow or Monday, uh, and we'll get a sense of where we're at. Um, so in the meantime, we've knocked out chapters 20 through 22. And that's the material on test 2. So that's going to happen next week. Hopefully, I'll get that thing live probably by Wednesday, and it'll be due by the end of the week. So if you haven't already started doing those chapter 22 homeworks, you should definitely get on those. They're going to come due sooner than later. Meanwhile, we do have to move on. And the next chapter is chapter 23. And chapter 23 is going to introduce Faraday's law of induction. And that's going to be an important place because it's going to show us that there's a relationship between the electric fields that we learned about back in chapter 18 and the magnetic fields that we learned about in chapter 22. Now, if you recall, when we first started talking about electric fields and magnetic fields, the thing that I had said was that electric fields get caused by charges because those charges exist. If you have a charge, it creates this disturbance around it that we call the electric field that creates the Coulomb force. And then magnetic fields, by comparison, those get created when charges move. So electric fields existing creates electric fields. Charges existing creates electric fields. Charges moving creates magnetic fields. That was the way we sort of had talked about it at the time. And there are some exceptions to that. And that's what Faraday's law is about. Faraday's law is going to show us a second way that electric fields can come into existence. That's not simply about charge, but about something else. And to understand where this concept comes from, we have to kind of go back to the beginning. So, once upon a time, Michael Faraday, the guy we named the unit of capacitance after, in his lab noticed something weird. Why am I sharing that? I don't want to share that. I want to share something different. So, what Michael Faraday noticed as he was playing around with charges and such is that he had a coil of wire and he had a magnet, and he was measuring the voltage across his coil of wire, not unlike this. And of course, the wire wasn't connected to any kind of battery, so there should have been no voltage. He was not expecting any kind of voltage. However, as he's mucking around in the lab, he notices that when he moves this magnet around in the presence of the coil, he notices his voltmeter starts to jigger around. He's like, that's weird. It's like, what's up with that? Hang on, this is the crummy sim. Let's do this one. It's not really showing me the thing that I want to show you. There we go. Now you can see the needle moving a lot more noticeably. All right. So he's moving this magnet around, and as he does, he sees there's a voltage across that coil. He's like, that's weird. Is my magnetic field creating a voltage? That doesn't make any sense, because he has no reason to believe that it should. And what's more, he figures out that it's not really just about how much magnetic field he's got, because he notices that when he takes his magnet and he puts it inside the coil, you see how he got that little momentary burst with a very large voltage? But then the voltage goes away. And he's thinking, this doesn't make any sense, because I've got a whole lot of magnetic field right here in this region inside that coil, and yet I'm not generating any voltage. But the minute he takes the magnet and pulls it away, oh my God, huge voltage spike. When he puts it back in, huge voltage spike. Notice when I pull it out, I get one voltage direction. When I put it back in, I get another voltage direction. And Faraday's seeing all this, and he realizes that there's something new going on, something that's worth investigating. But he doesn't yet know what this is. And so what he has to do is he's got to build some sort of model for explaining this weird physics that he's seeing. And it was from that model that we would eventually derive what would come to be known as Faraday's law of induction. Now, in order to understand Faraday's law, I've got to introduce some terminology that Faraday used to explain this weird phenomena that he had observed. And the way we'll do that, let me switch back to the document camera for a moment. Oh, that was me. Let's not do that. Level of zoom there. All right, so what Faraday needed to introduce is I got a lot of stuff running. I'm gonna close some windows. All right, so what he realized was that he needed to talk about something that we're going to call our magnetic flux. Hang on, my computer is acting funky. Oh dear. Wow, that was wild. All right. So, I'm not sure if I just interrupted the meeting there or not, but that was pretty crazy. I hope that this is still says it's still recording. I don't think it ever interrupted the session. But all right. Let's try that again. So, in order to understand Faraday's law of induction, you have to understand the following concept. And it's called the concept of magnetic, not electric, flux. Now, the basic idea of magnetic flux is that we're essentially counting the number of field lines that penetrate some surface. So if you imagine, here is some region of space. Here's some circular region. And imagine there's a magnetic field sort of in that region. And what's going to happen is there may be magnetic field lines kind of bending around. Imagine these are my B field lines. Now, these magnetic field lines don't actually penetrate that surface. They don't go through that region. But, here's a line that comes in through the bottom and out through the top. Here's one that comes in through the bottom, out through the top, into the bottom, out through the top, into the bottom, out through the top. And then these miss entirely. So the idea is, I'm trying to draw this in like 3D. So imagine these are underneath the thing and these are coming out the top. So what's going to happen is magnetic flux would be simply a matter of counting how many lines go through this region and keeping track of them. That's literally the idea, counting magnetic field lines that penetrate a surface. And if I were to try to measure or to calculate what that would be, it's pretty clear that the amount of magnetic flux would depend on a few factors, right? Factor number one would just be the size of the region through which I'm calculating the flux. If I had drawn this circle bigger, I would have got more lines, right? If I'd drawn the circle out to here, it would have caught all these lines going through it. So it is clear that the magnetic flux is going to depend on the area of the surface through which we take the magnetic flux. If I have a bigger area, I'm going to get more flux. That's kind of a no-duh sort of conclusion. Now, the other thing it's going to depend on is the strength of the magnetic field. Here's how I know that it's going to depend on the strength of the magnetic field. So if the magnetic field is stronger, the way that I would illustrate that is, remember that the magnitude of my vector depends on the density of the lines. So if I had a stronger magnetic field, I would draw my lines more tighter together. Or in this case, I would just draw more lines. But you'll notice, if I'm drawing more lines, I'm going to have a lot more lines go through that region. So clearly, larger magnetic fields are going to create more flux than smaller magnetic fields. That's kind of obvious. Now, the trickiest one to wrap your head around would be the orientation of your surface relative to the magnetic field. So what does that even mean? So what I mean by that is, let's flip this around and imagine that I've got a uniform magnetic field. So I've got some region of space where the magnetic field is uniform. It's evenly spaced. Now, if I have some, let's say, rectangular surface, and I lay it out like so, I'm going to have several lines penetrate that surface. They'll come in the bottom, come out the top. But what would happen if I take that surface and I rotate it 90 degrees? Now, what's going to happen is I got lines that miss it on one side, that miss it on the other side. And in fact, if my surface is super thin, then what's going to happen is it's like taking, this guy here and laying it on its side. You hardly see anything. The lines would just go straight from one side to the other. You wouldn't get any flux. No lines would penetrate that surface if I tilted the edge towards the field lines. So what's going to happen is if you change the orientation of the surface, you're going to get a different amount of flux. And so to put all this together mathematically, here's how we're going to define flux. This is where the definition of flux is going to come from. And for the symbol for flux, we're going to use the capital Greek letter phi. Please note it is not phi, Mr. Fraternity people. It is phi. And this, the magnetic flux, is going to be the dot product of the magnetic field vector with the area vector. Now, you might be thinking to yourself, Tom, what the heck is an area vector? How is area a vector? And to make sense of what an area vector is, the magnitude of the area vector is obvious. It's the area of your surface. So if my little white laminated sheet here is the surface that I'm talking about, then it would obviously be this dimension times this dimension. That's length times width. That's what the area is. But for it to be a vector, there has to be a direction associated with it. So what would the direction of a flat sheet of paper be? Well, in order to specify that, we will say that the direction of the area vector is pointing perpendicular to the surface. So if this flat sheet of laminated paper is my surface, then the area vector would point straight up towards the camera. Now, alternatively, it could be straight back away from the camera, like into the table underneath it. Either of those work. So when you choose one orientation or the other, it's kind of like you're choosing which side to call the front, which side to call the back. So, the area vector points out the front or in the back. It's one side or the other. And that choice is fairly arbitrary. It's like choosing a coordinate system. But that's the idea. The area vector points perpendicular to my surface. So therefore, it's just like this. And so notice in my little stupid sketch here, my magnetic field points straight up. My area vector would also be pointing straight up. And if you recall from physics 1, when you do this kind of dot product where you multiply two vectors together but get a non-vector, the way you will handle that is you'll take the magnitude of B times the magnitude of A times the cosine of the angle between B and A. And you can see that that's going to give us the right sort of relationship, because in this example, my area vector points straight up, my magnetic field points straight up, the angle between them is 0 degrees, and the cosine of 0 is 1. So for this orientation of my surface, I'm going to have a lot of flux because it'll be B times A, some big number, times 1. However, in this case, when I rotate my area vector 90 degrees, well, now what's going to happen is the cosine of 90 is 0. So when I put the edge towards the magnetic field lines like such, I don't get any lines going through the surface. I get 0 flux. And obviously, if I was oriented at some in-between angle, well, what's going to happen is there were probably some lines that could have gone through this edge, but when I tilt it, they're going to miss now. So I'll get less flux from this than I got from this, but I'll get more flux from this than this. Notice that flux could be negative. What if I take this guy right here and I flip it 180 degrees around so that I basically turned it upside down? Well, now what's going to happen is my area vector would point straight down and my magnetic field would point straight up. The angle between that would be 180 degrees, and the cosine of 180 degrees is negative. So when you think about it that way, you can think of positive flux being a magnetic field line coming in from the back of the sheet and coming out the front, whereas negative flux would just be the magnetic field lines coming in the front and coming out the back. So if you think of one side of the thing being the front versus the back, that's what the difference would entail. Usually we'll just define our area vector so that it becomes positive because it doesn't especially matter. But that's how that will work. So now that we've defined this concept of magnetic flux, how is this going to help us explain what Faraday had observed when he did his early experiments? So what Faraday is noticing, and let's shift back to my simulation for this. Oh, I had to close my browser. Let's hope I don't crash out again. That would be very frustrating. All right, so here's what Faraday is noticing. All right, he's got this coil of wire, and of course, that magnet is creating a magnetic field. Conventionally, the magnetic field lines come out of the North Pole and they come back into the South Pole. So if you could visualize what the magnetic field lines look like, that's what they would look like. So right now, what's going to happen is if I take my surface to be the surface of this coil, what's going to happen is I'm going to have some of my magnetic field lines currently coming out here and going through that coil. Others, however, are missing. So right now, the amount of flux that I'm generating is relatively small because there aren't very many lines that go through this coil. Many of the lines are missing. However, when I bring this guy in here like that, well, now what's going to happen is basically all these magnetic field lines go right through the middle of that coil. So I would be generating a large amount of magnetic flux when my magnet is here in the middle of the coil, and comparatively less when I pull it back. And so what Faraday realizes is that this voltage that he's observing, it isn't about how much flux he's got, because right now I'm getting no voltage at all, but a whole lot of flux. So the amount of flux is not the key point in this scenario. Instead, what he's looking at is a voltage that depends on how much that flux is changing. If I go from having a whole lot of flux to very little flux, I get a spike. If I go from having very little flux to a big flux, I get a spike. So it's spiking every time the amount of flux through that coil changes. And what's more, when that change occurs quickly, I get a bigger spike than when that change occurs slowly. So watch, I'll go from having very little flux to having a lot of flux, but I'll do it quickly. Boom. Huge swings, right? Now, what happens if I do this same trick and I do it very, very gradually? So now I'm gradually doing it. Notice the flux is getting bigger, it's getting bigger, it's getting bigger, it's getting bigger, it's getting bigger. You can see the needle moving, but because I'm moving pretty slowly, I never saw much of a swing. So what Faraday realizes is that this voltage that he's measuring is related to the rate of change of the magnetic flux. Cool. So that's what he does. He formalizes this And thus is born the concept of Faraday's law of induction, which, if we write it out, says that so there's some terminology that we're going to have to get clear. If I look at the rate of change, the change in flux over time, there's a minus sign there. We'll think about that in a minute. That's going to give me what we call an induced EMF, which is a voltage. So I got to do this quickly. My wife is out of the house right now, but she could come home at any minute. I'm going to get in trouble for this. I tell this stupid story every year. So my wife is a huge fan of all of those ghost hunter shows. There's a gazillion of them: Ghost Hunters, Ghost Adventures, Ghost Incorporated. I don't know. There's a million of these stupid shows, and like 90% of them are on my DVR right now. She loves them, but she can't watch these shows when I'm home because when she does, I have to mercilessly make fun of them. And the reason I have to mercilessly make fun of them has to do with these guys not understanding Faraday's law. So every time these guys go and they hunt for ghosts, what they will end up doing is there's going to be some scene where they're in this like dark room of the haunted house, and they pull out a device called an EMF detector. And every time they pull out the EMF detector for the first time in an episode, they always cut to the one ghost hunter explaining how stuff works. And invariably, they'll cut to him, and the plumber guy, because they're plumbers in their day job, will be like, well, EMF stands for electromagnetic field, and it's believed that when spirits manifest, they will sometimes create EMFs and blah, 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 blah. I don't know, something stupid like that. So every time he does that, I cringe. Because first of all, EMF does not stand for electromagnetic field. That is not what it means. That is not how it works. EMF stands for electromotive force. And it's one of those silly terms that we picked up in the 1800s before we knew what was going on. It's really annoying. It's not a really great choice of terminology, mainly because it's not actually a force, right? Forces are measured in newtons, voltages are measured in volts. But the name kind of stuck from back in the day. But it's just a fancy schmancy word for a potential difference, particularly in this case, a potential difference induced by some source that's due to Faraday's law. So oftentimes we'll talk about the EMF of a battery being 1.5 volts. The EMF created by an induced coil would be an induced EMF, but EMFs are terms that get used in other contexts quite often. It does not mean electromagnetic field. So in any case, what happens is these ghost hunters will pull out these EMF detectors, and they're down in the dark room, and usually they're talking to the ghosts. Ghosts, if you can hear me, make yourself known. And then they're watching the EMF detector, and they're waiting to see like the number change on the EMF detector. And when it goes up, like, oh my God, there's a ghost, we're so scared, right? They go through this whole big theatrical deal about this little stupid number changing on their detector. Except here's what the ghost hunters don't seem to tell you. Because if you look inside that EMF detector, if you look at what's inside the little handheld box that these guys are waving around, what that box is basically this. This device is an EMF detector. What does it consist of? It consists of a coil and a thing to measure voltage. That's literally all it is. And so what's happening is if you take a magnet or a magnetic field and you allow it to change in the presence of that little coil, you're going to get a spike. But notice right now, I'm keeping the coil stationary and I'm moving the magnet relative to it. I could do this just as easily the other way around. What if I kept the magnet stationary and I move the coil around? It would be the same kind of deal. You'll get little spikes on your thing. What if I keep the coil stationary and something creating a magnetic field, like, I don't know, a piece of wire moves around? I'll get a little spike. And every time they pull them out, they're like, oh, well, this has to be ghosts because there's no magnetic fields down here in this haunted basement. And I'm like, no, dude, there's magnetic fields everywhere, right? Light is a magnetic field. The earth has a magnetic field. More importantly, your electrical equipment, the stuff you brought down with you to record all of what you're doing, well, they have current flowing through them. They generate magnetic fields. And if the magnetic field in one part of the basement is one value and it's a different value in another part of the basement, and you're moving your little meter back and forth, as you move it, you're going to get a voltage, right? That's how Faraday's law works. If you're holding your little meter steady and the camera guy moves around you, the magnetic field that he's generating will be different when he's in one position than when he's in another position. You're going to get a little spike. So what these guys are doing is they're sitting in the basement holding this stupid coil, and they're freaking out about this little needle jumping, but they're the ones making the needle jump, right? That's what they're literally measuring. It has nothing to do with ghosts. It has everything to do with magnetic fields. Oh, she just got home. We finished this just in time. Woo! That was a close call. Hi, sweetheart. I love you. Nothing at all. So, she's giving me a dirty look. I'm really glad she didn't walk in 5 minutes earlier.
You're recording this or talking to actual students?
Oh no, I'm recording my class session. All right. So, in any case, that's how Faraday's law works. So, what does that mean for us? Well, it means that I can generate voltages the same way a battery would, and all I got to do is take a magnetic field and have it change over time. So, why do we care? I mean, it seems kind of, weird and arcane. Yay, moving magnets around can generate magnetic fields, but it's going to end up having a lot of impacts. Now, before I get too deep into what those impacts are, I do want to at least address that minus sign. All right. Let's go back to my document camper for a second. So, what's going to happen is in Faraday's law, we find out that you generate a voltage that is proportional to the rate of change of your flux. But this minus sign is perhaps the hardest thing for a lot of students to wrap their heads around. And it shouldn't be. It's not that complicated. It's also the only place in physics that I can recall where a minus sign has a name, right? This minus sign is the representation of something called Lenz's law. And what that minus sign tells you is that this induced EMF, this induced voltage that we're going to generate, it always opposes the change in flux. Now, what that means conceptually is that if you've got a certain amount of flux and the flux tries to get bigger, the induced EMF is going to be in a direction that tries to keep the magnetic flux from getting bigger. It wants the magnetic flux to stay the same. Now, if you've got that coil and you try to make the magnetic flux in it smaller, the induced EMF is going to be the other direction. It's going to try to boost the flux up to keep it from dropping. So that's what that minus sign represents, is that anytime you try to make the flux change, the EMF in the coil is going to fight you and try to keep it from changing. That's what's going to happen. Now, bear in mind, it can't ever win. Imagine that you had a flux in a coil and you tried to make that flux bigger. and the coil fought you to keep you from making it bigger, and it was successful. Well, if it were successful, there would be no change. And if there were no change, there would be no voltage. But if there were no voltage, then it would not be fighting you, and you would have won. Does that make sense? So it always is going to make it harder to change, but it can never actually prevent the change from happening. It just makes the change often happen more slowly or less completely. But the EMF, by its very nature, will oppose that change. So let's do a concrete example, because this is pretty doggone difficult to wrap your head around. So here's my scenario. I've got this little loop of wire, right? And I could carry EMFs around this little loop of wire. And what I'm going to do is I'm going to take a bar magnet with the North Pole up and the South Pole down. And of course, remember the direction of my magnetic field for a bar magnet. I'm going to draw it to the side here because I don't want to get my other drawing too messy, right? Is that you can imagine the magnetic field coming out the North Pole, swirling around. Here's the arrows. Coming out the North Pole, swirling around. All right, so conceptually, that's what the magnetic field of a bar magnet looks like, right? So in the middle of the magnet, it's going straight up the middle. Out here, it's going straight down. And we're going to simplify this just by kind of ignoring the weaker fields on the outsides and thinking of this bar magnet as being a magnetic field that just basically points from south to north. So imagine this is the magnetic field, the simplified version of that sketch. So that's what we have over here. I've got a magnetic field that basically points straight up. Now, what's going to happen is when I'm close to the magnet, it's probably straight up and big, but further away from the magnet, it's still straight up, but it's smaller. So down here, I've got probably a tiny little amount of magnetic field. Up here, I've got quite a lot of magnetic field. So right now, I've got a tiny magnetic field in a really big area. So I'm going to start off with a small amount of flux, and that flux is pointing straight up. So we would say that it's in the positive direction, right? But what's going to happen is, as this guy drops down and gets closer, well, later on, if this is my loop, later on when the magnet is, say, right here in the middle, well, now what's going to happen is the amount of flux going through this surface is this big. So I went from having a tiny little B initial to a much larger B final. We would say that there is a change in the flux from beginning to end. Now, what direction would that change be? Well, I went from up a little bit to up a lot. The change in my flux would be upward. Now, what's going to happen is Faraday's law says that the induced EMF will oppose the change in flux. So the induced EMF wants to create a magnetic field to cancel out this change. And it wants that created magnetic field to be in the opposite direction. So obviously, the induced EMF wants to create a magnetic field in the opposite direction, right? Now, how would a coil of wire generate a magnetic field that's downward? Well, we know that if I have a coil of wire, if I induce a voltage, there'll be currents, and the currents are either going to go clockwise or counterclockwise. But if they go around clockwise as viewed from above, the magnetic field would point downward. I'm doing the right-hand rule. I'm curling my fingers in the direction of the current, which is the same as the direction of the EMF, and my thumb points in the direction of the magnetic field. So if my induced EMF wraps around like that, that will generate this required induced magnetic field, which will try to fight the change. And so that's what's going to happen. So as this thing falls toward my loop, I'm going to get an EMF and therefore currents flowing around clockwise as viewed from above. And that's what Lenz's law tells me, is that they're going to flow clockwise rather than counterclockwise. Now, what would happen if I let this magnet drop all the way through the middle and out the bottom? Well, let's flip it around. So now what's going to happen is when I had my little magnet that was right there in the middle, I had a pretty strong magnetic field right there in the middle. So my B initial is pretty big. However, after I drop it through, now my magnet is down here. Notice the magnetic field still points upward, but the magnetic field caused by this in this region is going to be upward but tiny. So now the change in my flux is from big to small, so the change is negative, it's downward. Now, what that means is that my induced EMF wants to fight the change. And it's trying to boost the field up to keep it big. Now, how am I going to do that? How would I generate a magnetic field that points upward? Take your right hand, stick your thumb in the direction of the induced field you want. Your fingers would have to curl around. And you can see that once this thing falls through the middle and drops down the bottom, the direction of my induced EMF will turn from clockwise to counterclockwise. So in order to figure out these sorts of questions, you're always going to have to break it down that sort of way. Ask yourself, what direction is the change in flux? Because the induced EMF will always be fighting that change in flux. So I'll either get a clockwise or a counterclockwise EMF, depending on what's happening in my situation. And we were seeing the same thing in the simulation earlier. When I bring the magnet in, I get a spike in one direction. When I pull the magnet out, I get a spike in the other direction. In each case, it's trying to maintain the flux inside that coil. So it's doing whatever it can to keep the flux from getting bigger or to keep the flux from getting smaller. Now, let's think about the mechanics of this for a second. Let's go back to this scenario. Now, as this magnet is dropping towards my coil, well, what's going to happen is I'm getting this induced EMF that is clockwise. And that clockwise EMF is generating a magnetic field created by the coil that points downward. But wait a second. Let's think about that in terms of like north and south poles for a second. By sending a current through that wire, the wire is kind of acting like a magnet. And if it's creating a magnetic field that is downward, then that's like having a magnet whose north pole is on the bottom and whose south pole is on the top. So what effect is that going to have on my falling magnet? Well, the magnet that I'm dropping has the south pole on the bottom, and my magnet being created by the coil has the south pole on the top. So when I put the south pole of this next to the south pole of that, what's going to happen is there's going to be a repulsive force. So this magnet, as it's falling, if it was just falling through like empty space, the acceleration would be 9.8, right? The acceleration of gravity. But what's going to happen is as it gets close to that coil, the coil is going to repel it. It's going to slow it down. And so the acceleration as it gets closer and closer and closer would stop being 9.8. It would be a little bit less because gravity's pulling it downward, but the magnet is pushing it back up. And so it would fall more slowly than you expected as it's coming down through the bottom. Now, you might think that when it goes through the middle and pops out the other side, you might expect that it would speed up, but you would be wrong. Because now what's going to happen is once it has passed all the way through and the direction of my EMF has changed, Well, now my induced magnetic field is upward. That means my magnetic field is upward. But if that's the case, if my magnetic field points upward, then the north side is up here and the south side is right here. So the magnetic field of my loop has flipped as the thing goes through the middle and falls out the bottom. But now what's going to happen is the south pole of my loop is next to the north pole of my falling magnet. They're going to attract. So even after it falls through the middle, what's going to happen is it's going to be pulling it upward. It's going to slow it down there as well. So if you were to watch this happen, if I were to drop this magnet through the loop, then it would be slowing the magnet down the entire way. Now, it can't ever quite stop it, because if it slowed it down enough to make it stop, then the flux would stop changing. If the flux stopped changing, there would not be an induced magnetic field, and the magnetic field created by the loop would vanish, and it would start to fall again normally. So it'll slow it down, but it never can quite stop it. So we were still in the classroom. There's usually a demonstration where I demonstrate this. I have a big long tube, and I'll drop two objects that are identical through them. The only difference is that one of those objects is a magnet, the other one is not. And when you drop the regular one through, it just goes thunk all the way through the bottom of the tube, just like normal. But when you take the magnet and drop it through, what happens is the tube is made out of metal. It's aluminum, so it's not a metal that would respond to magnetism. It's a diamagnet, right? So it doesn't really care. And as you drop the thing through, because the part of the tube below it is acting like this, generating a induced EMF in the clockwise direction, that's repelling the object. The part of the tube that's above it is generating EMFs in a counterclockwise direction. And as a result, you take that magnet, drop it through the tube, and you wait, 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 because it's slowing down and it won't fall at 9.8. And it takes several seconds to drop through the entire tube. Right? So it sucks you can't see that demonstration. It's pretty neat. But that's what's happening. So one way to think about why it's happening like that is in terms of energy conservation, right? Because think about it this way. I got a wire, right? There's no battery hooked up to that wire. And so if I'm going to send voltages around that wire, if I'm going to generate some current, that takes energy, right? It takes energy to send currents through that loop. But where would that energy even come from, right? The energy doesn't just come out of nowhere. Energy is conserved, right? So if I'm going to have energy to send current around this stupid loop, I've got to get that energy from someplace. And where does the energy come from? It's coming from the kinetic energy that I'm not getting in the falling magnet. It should have been falling faster, but now it's falling a little bit slower. And that missing kinetic energy is the energy that I'm using to generate those currents. So here's the really cool thing about Faraday's law. What Faraday's law is doing is it's allowing us to translate kinetic energy into electrical energy. That's where the energy comes from for these induced currents. That's pretty cool. Let's take that to its most ridiculous extreme. So obviously, with this guy over here, if I'm moving this back and forth, I can generate a lot of mechanical energy. Now, if I was actually doing this, I would actually feel a little bit of resistance. If I push it forward, I would find it harder to push it forward than normal, because I'm having to push against the magnetic field created by the wire. And that resistance that I'm feeling is the work I'm having to do, and that's turning into electrical energy. If I pull it back, it'd be harder to pull back than normal. And that extra work I have to do to pull it away is where the voltage is coming from. So what if I go to exploit this? What if, actually, I can just go this way. Yeah. I've already downloaded it. So check this out. This is awesome. So what if I did something like this? I got a coil. I've got a magnet, but I have my magnet set up so that I can make it spin, right? And all I've got to do now is just make that magnet spin. And what's going to happen is right now the magnet is facing south to north. So right now the magnetic field of this magnet is pointing to the right inside that coil. I've got a lot of flux, and that flux is to the right. However, when I rotate that magnet around 90 degrees, the magnetic field will be up and down. And that means that if I'm doing, B dot A, the angle between B and A, the area vector of this coil is to the right, B would be pointing up and down, the angle would be 90. So when I rotate this thing 90 degrees, I'm not getting any flux. When I rotate it around 180 degrees, now the magnetic field points to the left, the area vector pointed to the right. Now I'm going to have negative flux. So as I spin this thing around, I'm changing the flux from large positive to 0, to large negative to 0, and back again to large positive. So watch what happens when I rotate my magnet. Well, as the magnet rotates, I'm changing the magnetic field or the flux continuously, and therefore I'm getting a voltage continuously. If I look at it in terms of the voltmeter, what you can see is that my needle is swinging from positive to negative and back again. It's going positive for a while, then negative for a while, back and forth, back and forth. Now, since the induced voltage depends on the rate of change, if I spin it faster, I get bigger swings. So what's happening is by making this thing spin, I am generating electricity. This is actually how we do it. This is how we generate the electricity in our homes. Some of that electricity is quite literally created by flowing water. That's how hydroelectric dams work. What is a hydroelectric dam? You've got a magnet that can spin. You let the water from the dam flow through a sluice gate, and as you do, that water makes your magnet spin. That magnet is inside a coil, and as the magnet spins, you're creating flux that's constantly changing, and you get this voltage that swings positive, negative, positive, negative. It creates alternating current, which we've talked about previously. Notice if I spin it more slowly, I get a smaller voltage. If I spin it more quickly, I get a larger voltage. I can also change the voltage by doing some other stuff. If I had a bigger magnet, I'll get bigger swings. If I've got a wimpier magnet, I'll get smaller swings. So the bigger my magnet, the bigger my voltage is going to be. I can also do this by changing the area of my loops. If my loops are bigger, I get bigger swings. If I have more total loops, I get bigger swings. One way to think about that is that my area, like if I'm looking at a circular area like I have for these loops here, my area would be like pi r squared. But what's going to happen is that's just the area of one loop. Right now I have 3 loops. So I would have 3 times the effective area. I'd have flux through the first loop, then the second loop, and the third loop. So I just multiply by 3 to get the total flux. So that's where we're going to get alternating current. And every power plant in existence is using the same basic process. Obviously, hydroelectric dams spin your magnet by running water past them. But other power plants do the same thing. How does a nuclear reactor work? What does a nuclear reactor do to generate power? Well, inside a nuclear reactor, you've got a bunch of nuclear fuel. You take that nuclear fuel and you split those atoms. You allow those atoms to split. And when they do, they release energy. Now, when you take that energy and it releases, typically what they do in a nuclear power plant is you've got to cool your reactor down because it's releasing all this heat. If you don't, it's going to melt down. So when you take that heat away, what are you doing with it? You're usually absorbing it in some water. That water gets hot, it turns into steam. And when steam boils, it expands. So as it expands through a fan. That fan rotates. The rotating fan spins my magnet, and that generates my electricity. You go to a coal-powered power plant. How does a coal-powered power plant work? Well, you take some coal, you put it in a furnace and burn it. When you burn it, you generate some heat. That heat boils some water. The water expands, spins a turbine, spins my magnet, and now I've got alternating current. If you wanted to, you could run power plants off of your hamster wheels. You know, what do? You put your hamster in the wheel, the hamster runs on the wheel, connect that wheel to a magnet, the magnet will spin, and haha, I've generated some AC electrical current. In your car, right, you've got electrical devices. Where is the power from those electrical devices coming from? You might think it's your battery, but you'd be wrong. If you tried to run your car off the battery alone, your battery will die pretty doggone quickly. If you've ever done that, if you've left your lights on like overnight and your battery is dead the next morning, that's why. You don't have that much juice in your battery. So what actually happens is the battery in your car is really only used for the initial turning of the key, right? That provides the initial spark, but then what happens is inside your engine block, you're injecting some mixture of fuel and air into a cylinder. The initial spark from your battery causes that to ignite, and when it ignites, it blows up. It literally explodes, and it pushes that piston forward. That piston is connected to a crankshaft, which rotates, and inside something called your alternator, you've got a coil and some magnets, and that magnet will rotate around, generating electricity in your coil. And of course, your car is running off of this internal combustion, and by blowing up the fuel air mixture and causing that piston to rotate, you're generating electricity. And so once you get it going, the electricity in your car is being provided by that alternator. And in fact, your alternator is charging your battery back up for the next time you have to start your car. That's why if you ever have your battery die in your car and you have to jump yourself off, you have to leave your car running for a while. If you turned your car off immediately and then tried to start it again, it wouldn't start because your battery hasn't had time to charge back up. But by getting someone to jump you off and getting your engine running, now the gasoline is burning and it's going to use your alternator to generate some electricity. And some of that electricity goes to charging your battery back up. So after about 20 minutes or so, your battery is good to go. But that's what's happening. Every electrical power generation method that we use involves Faraday's law of induction. Now, let's put some math to this. Let's imagine I've got this silly generator, and I want to figure out how big these voltages are. Well, I can do that easily enough. So if I've got that generator scenario, and I've got some kind of coil, and then inside that coil, I've got a spinning magnet. What's going to happen is my magnet is rotating with some angular velocity, omega, where omega is measured in radians per second. We learned about angular velocity last semester, so hopefully you still remember. And what's going to happen is the flux generated by this would be whatever the strength of my magnet is, B, times the area of my coil, but I'd probably have to multiply that by how many coils I've got. So I'll multiply by N coils. So this is kind of like my actual area times the cosine of theta. Again, I'm just doing BA cosine theta. The N is coming back because I have area for each coil. I'm just multiplying by N. So that's my flux. Now, what's going to happen is as my thing spins, my flux is going to change. It's going to start off large because my area vector probably points straight up. My magnetic field starts out pointing straight up. So at first, this angle is 0. The cosine of 0 is 1. So I'm starting off with lots of flux. But after I've rotated 90 degrees, I'll have 0 flux. After I've rotated 180 degrees, I'll have negative flux, and so on and so forth. So this angle that I'm going to make is not going to stay zero. It's going to change with time. Fortunately, last semester when we did circular motion or rotation in chapter 10, we learned how to deal with that because we learned the angular position function. Hopefully that rings some bells. Now, what's going to happen is I've conveniently started out with my original angular position being zero, so I can be like, that's zero. And if I'm spinning it at a constant speed, the angular acceleration is zero, so that goes away. So theta is going to equal whatever angular velocity I've got, which is constant, times t. So I can replace this with BAN times the cosine of omega times t. So that tells me how much flux I've got at any given moment. But what I care about is how rapidly that flux is changing, right? Remember, the EMF is the rate of change of my flux. And to think about like the rate of change of my flux, let's do this visually. I've got my flux looks like this. Let's do a graph. Graphs are awesome. Here's time. Here's my flux. So at time zero, plug in zero for t, this is going to equal 1. So my flux at that moment is going to be whatever b times whatever a times whatever n is. So whatever that number is, it's right there. So at time zero, I've got that much flux. Now what's going to happen is this is going to be multiplied by this cosine function, and the cosine function is going to look like that. So the amount of flux that I have at any given moment is going to change like a cosine. It's going to go from BAN at the max. Down here, it's going to be negative BAN. And then there's going to be places where it crosses zero in between. But what I'm looking for is the rate of change of my flux. Now, how do I interpret the rate of change of my flux? Well, delta flux would be like the rise of my graph. Delta t would be like the run of my graph. So really what I'm looking at is the slope. So my induced EMF is going to be the opposite of the slope of that graph. But wait a second. At first, if I do the slope, and how do you do the slope of a curvy thing? You do a slope of a tangent line. Well, at first, this thing is horizontal. So right now, I've got a slope of 0 right at the very, very beginning. So initially, the slope is 0. But then it's getting steeper and steeper and steeper. Right here, the slope is going to be negative something. Right here, it's going to be negative something, and it's as steep as it ever gets. Then it starts to get more and more leveled off, and then I got a slope of 0 again. So my induced EMF is going to have to start out being 0. It's going to have to get super, super, super negative. Still negative, still negative. Then it's going to pass through 0. Then here, on this side, these are positive slopes. And here is a positive maximum. Here is a 0 again. So what's going to happen is my slope's going to have to look like something, and I can kind of sketch it out. So I'm starting off at 0. Now, my slope is big and big and negative. However, since the EMF is the opposite of my slope, if this slope is big and negative, here my value of the EMF has to get big and positive. Then it's going to pass through 0. Oh, look, big and negative. So that's going to go back to 0. Wait a second. What the heck did I just draw? What the heck is that pattern right there? It's a freaking sine function. Ha ha! Awesome. So that's pretty cool. So it turns out that my induced EMF is going to end up being some kind of freaky sine function. So if that's the case, hopefully I've at least motivated what's going to happen next without resorting to calculus. But what I can say is that my induced EMF is going to end up being B times A times N, and this is the part that you're not going to get, times omega times the sine of omega t. So this is not a calculus-based class, so this may not be obvious, but most of you guys who take this class have taken calculus, and what I'm doing right here, I mean, I'm talking about slopes, right? What are slopes? They're derivatives. I'm talking about rates of change. What are rates of change? They're derivatives. So what did I really just do? I took my flux and I took the derivative of it. That's what I did. What's the derivative of BAN cosine omega t? Well, I have to take the derivative of cosine, and the derivative of the cosine is negative sine, but the negative got canceled by this negative, so it became positive. But when you take the derivative of omega t, that's a function of a function. I have to take the chain rule and multiply by the derivative of the inside function, and the derivative of omega t with respect to t is omega. And that's where the extra omega came from, right? So, if you're looking to memorize stuff and you don't want to have to, just commit it to memory, if you can figure this part out, you can derive this by taking a derivative. If you don't know what I'm talking about right now, don't sweat it. Just know this, right? But that's what we just did. So what this tells me is the EMF of a generator. So if I'm, trying to figure out what voltage they're producing at the power plant where they're turning nuclear power into electrical energy, this is the way I'll do it. What does it depend on? Well, it's going to depend on how big the magnet is. It's going to depend on how big their coil is. It's going to depend on how many coils they've got. Omega is how fast you spin the coils. We saw that in the simulation earlier. The faster I spin it, the bigger the voltage swings were. But of course, the voltage that they generate is going to end up being an AC voltage. It's going to swing from some positive value to some negative value and back and forth, back and forth. So it's changing continuously. And omega is related to how rapidly it changes. Omega is called the angular frequency. And of course, it equals 2 pi times f, where f is the number of cycles you get per second. To give you a sense of how that works in our domestic power production, omega for those is about 60 hertz. That's the standard, at least here in the United States, is that we will get 60 of these cycles per second. And that tells me how fast I have to spin my magnet. I have to spin at that rate in order to make that work. So, yay. Now, 9 times out of 10, we're not going to care about the instantaneous voltage. We don't care what the voltage is at a particular moment. We often care about either what the maximum voltage is or what the RMS voltage is. We talked about that back in chapter 20. And you'll notice the sine of omega t part, that's just a number that's going to be at most 1. So the biggest my voltage ever gets is just this front part. This is my maximum EMF, or my maximum voltage from my generator. So as long as I know that, I can figure out the RMS voltage. Remember, the RMS voltage, this is back from chapter 20, I'm just reminding you, is that. So now we have a direct through line to, I'm spinning a magnet, I can figure out how big that voltage is, then I can use that to figure out the RMS voltage, and they're all interrelated. So, pretty nifty. So that's Faraday's law. at its core. This idea that when you take the flux through some surface, it will end up generating a voltage that tries to resist that change. And we'll play around with the implications of Faraday's law tomorrow. Well, I guess it'll be on Monday. The big picture that we're going to end up seeing is that we'll see this sort of effect in different scenarios, and we'll learn how to interpret what happens in those scenarios. But I think I'm going to leave that for the next lecture. All right, so hopefully that made some sense. Hopefully you guys aren't too demoralized after the exam. I will talk to you guys later. Hopefully see you tomorrow. Have a good one.